Hello, testing, testing. Hello, testing, testing. Okay, mic seems to be working. Hello, good morning, or afternoon, or evening, wherever you are. We're doing more Leetcoding today. More specifically, the TikTok questions. All right, let me get those questions up. Okay, last time we did up to where? We skipped a bunch of array stuff because we did it before, just last week. I think we did all the easy questions for binary tree. We also did validate binary search tree. We got through a lot yesterday. Okay, so next up would be binary tree level order traversal. Here we go. There is no more easy questions for binary search trees. Okay, binary tree level order traversal. Given the root of a binary tree, return the level order traversal of its nodes' values from left to right, level by level. Okay, so that's the input. The output is 3, 920, 15, 7. If the input is just 1, output is just a list of 1s. Let me hide my screen for a brief moment while I sign in. I feel like we just have to do sort of a breadth first search thing, right? With the queue. And then we have to keep track of our levels somehow. Maybe we'll do a child queue and a parent queue. I don't know. Okay, we back. Excuse me. Hold on, let me bust out my drawing tablet. Okay. I feel like we just need a queue, right? Maybe 2 queues. Let's say this is our queue number 1. So we put 3 in there first. And then we process 3. Do we need a second queue for this? I feel like it would be easier. Yeah. Because what if one layer's elements are mixed up with another layer's object? So let's say we process 3 and then we just dump 9 and 20. Oh, but wait, it's left to right, so we have to put 20 first and then 9. Ooh. We can put 20 there and then 9. And then we have to pop all of 20 stuff, so wait, no, we process 9 first because that's the first out of the queue. And then back in the first queue we can put none of its children, and then we process 20. We process we put 7 in first and then 15. Okay, so that's important to know. We process the right children first, right to left. I want to do a case where it's more complicated. Let's say it's like, let me do a screenshot. Okay, here's example 1, right? What if it's also like, I don't know, more children here. So it's like maybe 7, 10. What's it gonna look like? So Q1 we put 3. We process 3 and then we put 20 and then 9. We process 9, so we put 10, 7. Wait, that's not gonna work, is it? Oh, wait, hold on. It's a queue, so last in. No, so we start filling it from behind, so it's. Oh, we process the rightmost stuff first. Rightmost stuff. Hold on. This sounds kind of weird. Breadth first search. Oh, hey, Dragon. Dragon says breadth first search. Yeah, I'm trying to do something like breadth first search too. I'm having 2 queues right now. Because I want there to be a way to separate out the children from their parents. So we process 9 first, right? And then we do the. Wait, how do we do this? Do we actually process the right children first? Hold on, let's say I process 3 and. Let's say I process 3 in the queue first. Do I actually do 9 and then 20? And then in the first queue I process 9 first, which doesn't sound right. So it's left to right. If I use the same rule of right first, would it work? So I would have 10. Wait, am I following my own rule? I'm so confused right now. So let's say I have 3. I put 20 in first and then 9. That would be right first. And then for 20, I put right first, so 7 and then 15. And then I process 9, which is 10 and then 7. I mean, BFS normally uses Q. Yeah, I'm using a Q. I'm using 2 Qs though. Okay, would it be better to process it left to right then? Let's say I have 3 in the queue first. I process it, so I put 9 and then 20. Wait, left to right. So 9 first, and then 20. This doesn't sound correct. So I process 9 first, left to right, so 7, and then 10, and then I process 20, which is left to right, so 15. Oh wait, if I pop this off, it's the right order. 7, 10, 15, 7. 7, 10, 15, 7. Oh shoot, I got it, okay. We process it from left to right. I was wrong the first time. Okay. I'm thinking about using 2 queues because I want a way to separate all the children from their parents. I don't know, that's my thinking. Okay, let's try implementing this. So we are returning a list of lists. Okay. We need a queue of integer parents is equal to new linked list. Let's do another queue called children. It's equal to new linked list as well. I want to watch out for the null case too. If root is equal to null, then you return empty list. Yeah, probably empty list. Do they provide an example? Yeah, empty list. Return new array list. Linked list. It's better for appending apparently. Okay, now the hard part. The breadth first search part. Parents. Reggie says, hi, how are you doing? I am doing good. Yeah, today's been a good day. I didn't really do much today. I just got up, ate some raisin bread, and then now I'm here. Yeah, how are you doing, Reggie? Hope you're having a good day too. Maybe we'll add root to parents first. Reggie says, I'm good. Hey, good to hear. Reggie says, need to solve Leetcode too. Oh. Maybe you can solve it with me. I don't know what the stop case will be. Maybe while parents not empty. What the heck happened? Huh. While parents is not equal to empty, keep processing. Okay. So Reggie says I'm gonna do linked list questions. Hey, let's go. Tree node. I guess current node is equal to parents dot remove. I almost said pop, that's for stacks. We add all of its children into, yeah, children. If current node dot left is not equal to null, then you add it into children. Children.add left for node.left. Likewise, if the right child is not empty, you add it to children.add current node.write. I need to figure out a time to print or add into a solutions bank too. Okay, I need a results list too. I haven't really thought about how I'm going to do this. Result is equal to new list. Let's do linked list because it's faster for appending, allegedly. Okay. Maybe we'll add parents results.add. How do we add a duplicate of a linked list into results? Results.add parents.clone. Is that how you do it? Let me look up how to clone lists. Java, how to clone lists. How to clone a list in Java. New array list. Oh. You just use a constructor, huh? Wasn't there a clone? Oh, clone. Okay. Reggie says, do you able to solve the same question after a week? Sometimes no, but that's why I do review streams every now and then. So once I do it twice, maybe 3 times, then usually I can remember how to do it. I'm supposed to return. OBO says, be careful when cloning lists. There's a difference between deep cloning and just cloning. Oh, true. Oh, so if I just do a shallow clone, I'm still pointing to the same tree nodes, huh? It's not a copy of the tree nodes. I guess I'm thinking hard right now because I realize I need to return a list of integers. Right now it's a list of tree nodes, which is not ideal. Okay. Man, that's such a hassle though. I need to convert a tree node list into a integer list. Is it time for some stream operations? Is it worth breaking out stream operations in Leetcode? Obo says, sorry for backseating. Oh, no worries. That wasn't bad. Backseating is when you tell me exactly what to do for a problem. I don't think you've reached that level. Okay, so this is gonna be a hassle. I need to convert Should I do a helper function? Private list integer node list to int list. I just realized I typed these the wrong way too. What a hassle. Tree node. Tree node. Okay. A list of tree nodes. Node list. Okay, so we need a new list called, let's do a linked list. List integer int list is equal to new linked list for every single tree node, not plural, node in node list. Int list dot add and dot value. Okay. Okay, so results.add node list to int list. It seems like such a roundabout way of doing it. Parents. Okay. So if the parent is empty, that means we cleared a level, right? Time to start processing the next level. If parents dot is empty, then that means the list of children is complete. And we convert them to a list too, and then we add it to the results. Results.add level cleared. Results.add node list to int list. Children. Is that the best way of doing it? Maybe parents. Parents is now equal to children. And then we'll assign children equal to a new linked list. Okay. And then in the end, what if we have no new children though? It's just a empty linked list? Okay. Should we watch out for that here? So we could return an empty linked list here. So we have to watch out for, yeah, empty linked list. list integer to int list is equal to node list to int list parents if to int list dot is empty, then you add it into parents, or you add it into the results to int list, and then children equals new linked list. And then in the end, you just return results. Return results. Cool. I have a feeling that we've done some stuff backwards here. This will return a backwards list, right, of all the children, because the children will be like this in backwards order. We need to pop them up in a queue fashion. So we'll take a linked list instead, tree node linked list. So we'll have to go from backwards to front, huh? Yeah, backwards to front. And we can't pop them either because I think we still need the list for our traversal. Maybe it can still be a list. Or int I is equal from node list dot size -1, while I is greater than or equal to 0, I minus. Tree node current node is equal to node list dot get I and then in the int list we add current node dot value. All right, let's see how many compilation errors we have. Q tree node cannot be converted to list of tree node. Is a queue not a list? It's a linked list, right? Oh. Node list to... We should just do linked list, huh? Compilation error. Returning missing return statement. Return int list. Oh cool, we passed some cases but we missed some too. Wait, we passed all the simple cases. Okay, that's not good then. We're kind of close though. It's this case, right? So we got it backwards for some. $9.20 and then $15.7. Wait a minute, why is it backwards? Oh, we're adding it. How do you put stuff in a queue again? Is it push? Java, add to queue, add. Is a pure linked list add different? Linked list add. What's the default for a linked list? Oh, it adds to the last by default. That's not what we want. Can we force it to use the Q add? What if we just do add last? Linked list, Java, add last. Oh wait, add first? Add first. Okay, add first. That's probably what we need to do. Let's go. Okay, so this was kind of tricky because we force it to become a linked list, so it adds to the last instead when we do .add. Okay, let's see how many formal questions we get wrong. Wrong answer. No. What's up with this one? We got some backward stuff again. No. Okay, time to draw stuff again. What does this tree look like? We have a 1. Why am I so zoomed in? And then a 2, 3. Four null. So nothing there. And another null and then a 5. Okay, that makes sense. Then we want a 4 and 5 here. Why am I returning a... Why am I doing a 5, 4 then? Okay, let's say we're doing 2, 3, right? Or let's start from the front. Let's do parents. Parents, children. Parent starts with 1. And then we add it to the results. Let's do results is 1. While parent is not empty, current node is you process this one. If left is not equal to null, then you add first. Wait, we added to the first. 2. If right is not equal to null, then you add first right. Wait, that sounds wrong. Wait, add first. No, it's right. It's still a queue order. If parent's dot is empty, what's the default? What's the default behavior of remove? Linked list Java remove. Oh, it's removed from the head. Well, that sucks. I think that's what's wrong. Remove last, because we need to keep up with the queue thing. There we go. It beats 15%. Okay. So I ran into a lot of trouble with linked list behavior versus queue behavior, huh? Excuse me. Alright. How are other people doing this? I see a highly uploaded Java solution. They're doing pre-order traversal? What? If root is equal to null, return yes. If AL, that's just a new array list. Dot size is equal to L. Huh? 0. What? People are using DFS? What? Self.d is equal to oh my goodness, what? Commented code, easy to understand, okay. Oh, they're doing a key like me. Start level order traversal while queue is not empty. Process all the nodes at the current level. Get the next node. What's current level? Wait, what's current level? Current level is equal to new array list. Oh, they're doing an extra list like me to track current level. Traversal.add. Alright. Sure. Wow, okay. Now my solution beats 91% for some reason. Okay. All it took was a resubmission and no code changes. Very nice. I'm on top of the world once again. Why did I have to look through all those solutions when this one beats 91% the entire time? Sure, I'm satisfied with my solution. Next up we just did this one, so binary tree right side view. Let's do this one. But first, let me hydrate. Binary tree right side view. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you see ordered from top to bottom. At first glance, this doesn't seem too bad. Or is there a layer of complexity to this that I'm not seeing? Let's take the example, yeah? Don't I just keep taking the right node? Wait, hold on. This is a medium question. There's no way it would be this easy, right? There's probably something I'm missing. It cannot be this easy. I refuse to believe it. I will not believe it like Naruto. Okay. I return a list of integers. So I start from here. So I'm like, okay, I have a left and then I have a right. Oh wait, what if I don't have a right at all? Okay, we'll worry about that later, but... I guess we go here, the right, and then the right. Wait, hold on. I just thought of some stupid cases. 1, 2. Okay, so here we don't go right. There's no way we can go right, we go left. Do we just try to go right as much as possible? And then if we can't, we go left? Dude, I also just thought of another stupid case. Let's say we have 2, 3, 4. So my solution would be 1, 2, 4. Oh, dang it, this is hard. I see why this is a medium problem now. Because, let's say I'm looking from here, right? I have an eyeball here. Look, it's me. So I would be seeing this, and then this, and then this. No. Do we have to do another breadth first search? This is like that other problem, right? The one we just did. We do breadth first search, and then we take the rightmost element of each level. Yeah, that's what we do, huh? One more breadth first search, take the rightmost element of each level. Man, so much repeated work from last time. Can I just take what I did last time? I don't want to write so much code. Level order traversal. I must see if I can just modify what I just did here. Okay. I will try to work the smart way. Okay, if root is equal to null, then return empty. That's correct. That's my result, that's my parents. Root node. Okay, this has to be different. Node list to int list. We have to return the rightmost element, aka the last element. Right, the last element in the linked list. So parents dot remove last or get last. Does linked list have a get last? Java linked list get last. They do have a get last. Get last dot value. Okay, so no need for helper function anymore. We can just do get last. While parents is not empty, process it. If it is a left, get it. If parents is empty, That means you cleared a level and you have a complete children list. Complete children list. We'll have to do if parent is not empty. If parent is not empty, then results.add what we did here. That should be the way to go, right? Children is equal to new linked list, return results. Results.add parents.getLast.value. Hold up, I just remembered. The ordering is really weird, right? So this would be the ordering. If I had 7, 15, 10, another 7, 7, 15, 10, another 7. That's gonna be the... Ooh, I'm confused. Oh no. I should be taking the first, right? Let me do a test run. Int cannot be converted to... Oh. Result is just a list of integers, not a list of integers. Cannot find symbol, parent, more like parents. Wrong answer. What did I do? 1, 2, 5. Yeah, 1, 2, 5. It's the opposite. 1, 3, 4. Get first. It's looking kind of promising though. Case 2 and 3 passed. Hey, let's go. Basic test cases pass. Let's submit this thing. Let's go. We beat it 65% of everyone, allegedly. Very cool. Maybe I'll take a short breather right now. Yeah, how have you guys been doing? Have you guys seen any funny internet stuff recently? I've recently seen Mickey Mouse cover a Japanese song on Instagram. Hold on. I think it was the opening to that weird idol anime. Hold up. What was it called? Oh, Mickey Mouse sings Shinu no ga Iwa by Fujikaze. I swear I looped that song like at least 50 times because it's just so funny. Shinu no ga Iwa. The way he pronounces the words is really funny too. Watashi no saigo. Such strong emphasis on the saigo. But yeah, I've been looping that song if I'm feeling bored and I need a kick. Hey, thanks Dragon. Dragon says, let's go. Let's see, what else have I been up to? I have been watching more One Piece too. I finished Enies Lobby. Wait. I think I wrote down some notes for that too. What did I write? Enies Lobby was pretty solid from what I remember. Dragons' Water 7 is best chapter. Oh yeah, I agree. I enjoyed Water 7 a lot more than Enies Lobby. Enies Lobby is still pretty solid though. Yeah, it keeps me like relatively engaged. There was not really any point where I was like, oh, I'm bored, I want to stop watching. But I wasn't like, oh, I have to watch it, I'm so on edge. That was Water 7. Water 7 was like, dude, I can't stop watching, help. This story is actually pretty interesting. Oh wait, the death of the Medigo was sad though. I didn't know she would actually die. There has been no major deaths so far in One Piece, except for Maddie. Dude, when a apologizing ship makes you cry, you know this anime is good. No, I did not have my tissue ready. Nobody warned me it was going to happen, which is good because I was not spoiled. But yeah, Enies Lobby, not too many like super outstanding moments, but it was still pretty solid for me. Death of Medi was a highlight though. I'm currently on post Enies Lobby. Grandpa just visited. He's crazy. Oh wait, pink hair dude got a glow up too. That was pretty cool. And then blue hair cyborg dude is building them a new ship, which is pretty cool. Yeah, oh, his name is Frankie. Wait, yeah. Maddie's death though was so sad. Especially the way the VAs were all crying. Dude, the VAs in this show are so good at scream crying. They basically do a death metal scream when they cry sometimes. Like Luffy, Chopper. I think young Zoro also did a death metal cry too. It really hits different when they do that. Nobody cries like that in real life, but it makes those moments hit even more. Man, Maddie apologizing to the end while she was still sinking. And Luffy was like, I'm sorry, Sub did such a bad job fixing you. I'm sorry, Zoro and Sanji were being dumb and damaged too several times. Pretty comedic, but also pretty sad. Yeah, I enjoyed. Yeah. Water 7 is probably my favorite arc so far. It was... yeah, I was engaged all the way through. The fights were really good. He finally meets people that he couldn't beat. At least at first. Yeah, just the world was cool too. The introduction of trains on water, and also the city of Water 7 is just really cool too. CP9 was cool as villains. So yeah, I am on One Piece episode what? What's Enies Lobby? Enies Lobby, One Piece episodes 300 something, 312? Yeah, so I'm in the early 300s right now. I hear it's gonna start getting good soon. Water 7 was good, so I'm excited. I'm supposed to be getting close to the alleged time skip. Very exciting. Okay, Let's do more coding problems. Lowest common ancestor of a binary tree. Lowest common ancestor. Oh, let me hydrate first again. My mouth is dry as heck today. Given a binary tree, find the lowest common ancestor. Given 2 nodes in the tree, according to the definition of LCA on Wikipedia, the lowest common ancestor is defined between 2 nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Oh, we allow a node to be a descendant of itself. Okay. Example 1, we get this thing. Okay, these are the nodes that we need to find common ancestor for. Output is 3, 5, 1. Okay, fair enough. Example 2, 5, 4, 5, 4. Where's 5, 4? Oh, so it's 5? Yeah, 5. How the heck do we do this? I think I vaguely did a similar problem in the past. Maybe I can leverage my knowledge for this. Lowest common ancestor. I recall some prior knowledge for this. Lowest common ancestor. Okay, so we are given the root node and then PQ. How do we do this? So let's say we're on, let me just copy the example. Okay, let's say we're looking for 5 and 1, right? How did we know that we had to stop at 3? 5 and 1 are, I guess there are direct descendants, but that's not always the case. 1 could be at here or here too. So we can't rely on our direct children as indicators for this. Let's take a harder example, yeah? What if we have 7 and 4? What about 6 and 4? Sure, we'll do 6 and 4. What if we were looking for 6 and 4? 6, 4. So if we're looking at 3, we're like, oh, maybe we can do a depth first search of 6 and 4, and we're like, oh, 6 and 4 are all on our left side. Okay, so maybe we'll go to our left side. At 5. And we're like, oh, 6 and 4 are on different sides of me. I guess that's our most common ancestor, the first one where it's on the left and right side of me. Let's try a different example. What if we're looking for, let's add more nodes. 9, 11. What if we're looking for 7 and then 11? So we're like 3, 7, 11 are all on my left side, so I go to my left. Okay, 7 and 11 are all on my right side, so I go to my right. 7 and 11 are on different sides of me. So I go to, oh, then this is the answer. Okay. There's also the case where I can be there's also the case where the root can be the most common ancestor too, right? So maybe, let's say we're looking for 2 and 11. 2 would be the most... how do we figure this case out? So either if so 2 cases. The first case where the left and right, the 2 things we're looking for are on our left and right, or it's a root and a somewhere else. I guess we'll have to watch out for that. Okay. Do we do this recursively? Is this possible recursive? Okay. So the root we do... I guess we look base case. Base case is if it satisfies any of this, then we return root.value. And else, if both targets are on the left side, we go to the left. Both on left. Then you recurse. Function on root.left. Everything else is the same. Both on right. Then we search root.right. Holy, my handwriting is atrocious. Yeah. And you return these. Okay, I have a strat now. Let's go. Okay, I think we can do something where okay, so one of the base cases is if one of them is my root, then I return. If root is equal to p or root is equal to q, then you return the tree node of root. Okay, now you have to figure out which sides the targets are on. So Boolean on left, I guess. Excuse me. We'll make a helper function. We'll pass in root and p. That's the target for now. Boolean p on left. Boolean p on right is equal to on. We can just do not on left, right? Root, comma, q. Wait, this doesn't make sense. Q on left. Okay, and if they're both different, one is true, one is false, that means one is on the left and one is on the right. And that's our second base case. If p on the left is not equal to q on left, aka different sides, return root. Okay. If they're both on the left, then we recurse on the left child. If p on left and q on right, return recursive call root dot left. I typed that variable name wrong. Root dot left, p and q are the same. And else that means both of them are on the right. And you make the same recursive call, but with the right child this time. Okay. And then all we need to do is work on the helper method, p on left. We can just do a depth first search, right? Private, Boolean, on left, where we have a tree node, a root, and tree node target. So we return Boolean. Let's do a DFS on root and target. Root dot left. DFS if root is equal to null, then we return false. If root is equal to target, return true, and else return depth first search. I guess the left side first. Root dot left target, or DFS root dot right with the same target. Does this work? I haven't done a DFS in so long. Root is null, return false. I think that makes sense, because we never found it. If root is equal to target, then return true automatically, no need to recurse anymore. Else return root dot left target, or DFS root.right target. Okay. My confidence is pretty low on this one. Let's run it. Missing semicolon. No, wrong answer. I mean, we got the dumb case working. 1 and 2. That's the base case. This is the example, no? 7 and 4 would be, we expect 3. Oh, P and Q is 5 and 1. We expect 3. What did I return? I outputted 5. Expected 3. P and Q is 5 and 1. Well, yeah, it should be 3. Did I not? Uh-oh, are these on? Oh. Does this work? I shouldn't have put a not operator there. Yay, it worked. Accepted. Let's go. It beat it 5%. I think we can add some caching on DFS, yeah? We probably do a lot of repeat work. Yeah, caching would be useful. What would the cache be on though? The root? Probably the identity of the tree node, huh? Or is it the target from the root? Is it possible for the nodes to repeat? Oh, all node.value are unique. Okay, we can do ooh, what can we do? Basically, the key can be 2 integers. No need to store tree nodes. Should we do a hash map? That sounds like such a hassle though. Okay, we put our original function here. We have a hash map. We have a hash map of a list of integer mapped to a boolean, I think. Boolean, yeah. And we call it cash. Cash money. I think we should just pass into the cache here, or pass it into the DFS calls cache. Yeah. Okay. Here we will also take a hash map of the cache. Ooh, this is getting kind of bloated with the caching. Insert the cache here. Okay, so another base case would be if we need to construct the key list integer key is equal to new array list key dot add root key dot add target. Okay, base case. If cache dot contains key, then you return the key value. Return cache dot get key. Okay, and then the result boolean is equal to that. You store it in the cache before you return a cache dot add key comma result return result. Okay. And then in the original method, we need to construct our hash map. Is equal to new hash map, and then we return the helper method with root pq cache. Man, that was a lot of changes. Tree node cannot be converted to integer. Line 24. Root.value, target.value, cache.contains, contains key. Let me guess, this is put. Add the cache here again. Add the cache here. Hey, it worked. Did we actually have any cache hits? Let me check. System.out.println cache hit. We have like no cache hits. Oh, wait. Huh. Do we actually not have any? That's weird. I mean, these were all 0 seconds regardless. I mean, it just had a 3 here. That's like a nothing case. 5-4. So we just... Let me try submitting this. Memory exceeded. Oh no. Is caching not the way to go here? That's a huge tree. Okay. Maybe storing all that is a bad idea. Okay, you know what? I'll just revert my changes. I'll be happy with what I had. Cool. Oh, Java DFS beats 100%. Oh, this is really short. Okay, if root is equal to p, return yes, that makes sense. Tree node is equal to left, lowest common ancestor. If left is not equal to null and right is not equal to null, return root. Right, okay, so if one is on my left side and one is on my right side, then I am the root. If left is equal to null, left is null, then right can be P or Q. Else return left. No way, I don't get it. Okay, you do a recursive call, where if we ever get P or Q, we return it. Hold on, they wrote an explanation, right? Recursively explore the left subtree to find P or Q. Recursively explore the right subtree to find P or Q. Oh, okay, so these could... There's a chance that these are not P or Q exactly. They could hit this base case too. Okay. I'm noticing that they don't have to do a DFS, because I guess I'm already doing a DFS with this. In the traversal, whenever we get the P or Q, we return it. If null, we simply return null. Should I try this? Okay. If root is equal to P or root is equal to Q, then return root. Yes, that makes sense. We don't need these DFS calls. Okay, so we make recursive calls on root.left and root.right. That's, yeah, because we're basically doing a DFS search anyways, right? So no need for this. Tree node left is equal to this. Right is equal to this. Okay, so if left is not equal to null and right is not equal to null, not equal to null, then that means we found P and Q on either side. Found P and Q on either side, then we return the root because it's on two opposite sides. If left is equal to null, then that means we only found them on the left side. So we return the left, the LCA on the left. If root is equal to null, because we're doing a DFS now, right? Return null. Else you return what you found on the right. Oh, not equal to null. Yeah, that's all you need, right? No need for these helper functions. Run it. Accepted. Yeah, we were doing a lot of repetitive DFS, right? While we were already doing DFS. And it beats 57%. Very nice. Very big improvement. Yeah, no need for caching too, right? Because we go through every element just once in the tree. Okay, let me note this down. This is called lowest common ancestor of a binary tree. No need extra DFS. Okay, I've noted this question down so I can review in the future. All right, I have something at 11 o'clock. Right now it's almost 10:40 a.m. in my area, so I need to leave soon. Is it gonna change if I submit again? Wow. Now it beats 100%. And all it took was another submission too. I am on top of the world, woo. Man, Leetcode is sometimes inconsistent with its timing, with its time calculations, huh? One submission, just one button click is all it takes to beat the world. you could be in the bottom 1%, and you click submit again, you beat 100%. Alright then. Alright, I'm gonna drop off for today then. I have stuff at 11. Bye guys. Thanks Dragon for keeping me company. Thanks OBO for stopping by. Bye.